frequency, we will measure the linear density of a string and find the tension it needs in order to reach the desired frequency.
The experiment will be possible by using the equation of the frequency is equal to the number of nodes over 2 times the length. All of this multiplied by the square root of the tension over linear density.
By knowing the frequency we want to reach, the linear density of the string, and the length, tension will be the variable we will have to obtain. We will be doing so with a diddly bow we constructed ourselves.
So, by causing a disturbance in the string and with the help of a tuner, we will be able to prove if our calculations were correct or not. This will ultimately help us understand particularly the waves and resonance principles.
A wave is to move freely and gently back and forth or up and down, as by the action of air, currents, sea wheels, etc.
The frequency of any physical system or object is the number of cycles or vibrations undergone during 1 unit of time by a body in a periodic motion.
Tension is the pulling force exerted by a string, cable, or any similar object on another object. It's a magnitude, a force, and it's measured in newtons. Tension is a factor that can determine a certain frequency.
At last, linear density is a relation between mass and the length of a string. It consists in the quantity of kilograms the string weighs per each meter that it measures.
We constructed a diddly bow with a wooden board, a cube, some nails, a glass bottle, a string, and a pulley.
The linear density we obtained for the string was 2.62 times 10 to the minus 4 kilograms over meter. The first frequency we want to obtain is 440 Hz, so by solving for the tension, we obtained that the weight necessary was 5 kilograms.
The second frequency we want to obtain is 392 Hz, so by solving for the tension, we obtained that the weight necessary was 3.89 kilograms.
As a conclusion, we can say that the waves rules pattern are: for each higher harmonic, we add a note to standing wave pattern. Between any two adjacent notes, there is an antidote where the oscillation amplitude is largest.
So for this activity, we were able to reach the frequencies of 440 Hz and 392 Hz.
By using a tuner, we demonstrated that the frequencies of A4, which would represent 440 Hz, and G4, being 392 Hz, were correct.
By modifying the tension, in this case the weight, and relating it with the calculations mentioned before, we accomplish similar results between the theoretical and experimental results.